Hey guys, I only got a few requests for this homework, so this shouldn't take too long. On number 15, we have two pieces here, a t and a natural log. So from my experience, we can't let the natural log part be the dv because there's no way to integrate that, not without actually using parts just on that piece. So when it comes to deciding deciding what u and what dv are going to be, our only option is to let the natural log part be our u. So our hands are kind of tied there. We're going to let u equal log t plus 1, and that means the t dt are all the dv. Remember, the dt or the dx, whatever it is, always has to be part of the dv. Okay, so now I want to differentiate this to get du. The derivative of a natural log is just the derivative of the argument, which is 1, divided by the argument, so t plus 1 dt. And then we're going to integrate this piece to get v. To get from dv back to v, you integrate dv, so that's just 1/2 t squared. And that's everything that you need. Now you just use the formula. I don't have it up here, but I trust it's in your notes somewhere. We're going to do u times v, so 1/2 t squared natural log t plus 1 minus the integral of v du. So let's see, and just to get junk out of the way, I'm going to put the 1/2 out front. Any coefficients can always be factored right out. You don't need it to mess up the integrand here. And I'm going to have what, a t squared over t plus 1 dt. All right, so now I'm thinking I know what the problem was. We don't really have a rule for this. I'm sure somebody, maybe 2 or 3 of you, did something wacky like rewrite this as t squared over t. Whoop, my daughter got a hold of the blue marker, that's done. T squared over t is t, and t squared over 1 is t squared. So somebody probably did that. And this is the point in class where I'd start yelling at you, because you can't do that. You can't do that. If you had something like t plus 1 over t squared, then there's only one thing in the denominator, so each of the things in the numerator can be divided by the one thing in the denominator. But the way it's written here, you can't just divide the numerator by each individual term in the denominator. That's trash, don't do that. No form of u substitution is going to work out for us. So, if you remember, we have a whole bunch of tricks and techniques. You kind of had the right idea. If you did try dividing, you had the right idea, you were just doing it wrong. You want to do division. So anytime you have a rational expression like this and the log rule doesn't work, or any kind of other u substitution doesn't work, or it doesn't fit one of the like arc sine, arc cosine, arc tangent molds, if the top is at least as powerful as the bottom or more powerful, then just dividing is probably the trick you want to use. So I'm going to go off to the side here and just do good old-fashioned division. How many times does t go into t squared? T times. T times t is t squared. T times 1 is t. I want to change the signs here because I really want to subtract. They cancel, and I'm left with negative t. Now let's start again. T goes into negative t, negative 1 times. Negative 1 times all of this is going to be negative t minus 1. We'll change the signs. They cancel. I'm left with a remainder of 1. So I'm left with 1 over t plus 1. So t squared over t plus 1, all of that got turned into all of that. So back to here, I'm going to need a little more room, so let me slide over a little. instead of integrating this version of our expression, I'm going to integrate that one. So that's easy enough. T goes to 1/2 t squared minus the 1 goes to t. And now this rule, the integral, if I just do a little work on the side again, the integral of 1 over t plus 1. That's our log rule. The top is the derivative of the bottom already. So there's no, technically we're using u substitution, but there's no need to formalize it because it's simple enough. The top is the derivative of the bottom. So this integral is the natural log of the absolute value of the bottom. Sorry if this is getting a little sloppy and wobbly. Whoa. Okay, so that term is going to the natural log of the absolute value of t plus 1. Let's just chuck a plus c on this on the end there. And that's it. We could distribute the negative 1/2. I was thinking about tossing the 1/2 up here as an exponent, but I'm not going to bother. It wouldn't allow me to get rid of the absolute value bars anyway, so forget it. Just leave it out front, or refactor out a 1/4 from everything. Whatever you want to do. There's nothing wrong with this answer. You could definitely stop right there. So there you go. That's number 15. Number 25 here is a good candidate for the tabular method because I can tell we're probably going to need we're going to need parts more than one time. The x cubed part is going to be my u because we usually choose the piece that gets simpler as we differentiate it, and that's going to take a while to get to 0. So I feel like I'm going to have an x squared and a cosine in my next integral, and I'm just going to wind up using parts all over again. So I'm going to go over to the side and I'm going to just use the tabular method to bang out all of the u's and dv's all at one time. So u is going to start out as x cubed, then it's going to go to 3x squared, then 6x, 6, and then finally 0. dv starts out as sine, and that must have come from negative cosine, which came from negative sine, which came from cosine, which came from sine. Now I'm going to start with positive and swap the signs the whole way down, and then figure out which terms match up. And then I'm done, right? So I just have negative x cubed cosine plus 3x squared sine plus 6x cosine minus 6 sine. That's it. It's easy. If you use the tabular method, problems like that are really, really easy. If you haven't practiced the tabular method, you want to do that because you definitely don't want to be off on the side doing parts with u, du, v, and dv 4 or 5 different times. It's not worth it. Learn the tabular method. Okay, from looking at number 29, I get the feeling that this is going to be one of those problems like the last example that I did for you in the last video that kind of uses parts twice and then sort of doubles back on itself, and you wind up with the integral that you started with, one on each side of an equal sign. So you wind up being able to combine like terms. So let's just jump into u is going to be, actually in this case it sort of doesn't matter, so I'm just going to pick the exponential part. E to the negative 3x, which makes du negative 3 e to the negative 3x. All right, so the dv must be my sine part. And if I integrate that, technically it involves a little u substitution. There needs to be a 5 there, and then a 1/5 outside of the integral. So I know that's just going to integrate to 1/5. Sorry, I guess negative 1/5 cosine 5x. Make sense? Okay, so now we have our formula, just u times v, negative 1/5 e to the negative 3x cosine 5x minus the integral of, let's just make the negative 3 and negative 1/5 a positive 3/5, and I'll throw it out front. Like I said in the last problem, if you have coefficients, just get them out of your way. And I have e to the negative 3x cosine 5x. Okay. Kind of looks like what we started with. It's another problem that requires parts. So we're just going to sort of start over and let u equal the exponential part. So du will be negative 3e to the negative 3x dx. dv is the trig part, cosine 5x. So v must have been, let's see, 1/5 sine 5x. And now I'm just going to expand this. Be careful here. If you did factor that negative 3/5 or the 3/5 out, be sure that it's going to wind up getting distributed to the entire expansion of this integral. If you didn't bother factoring out and it's in here, then do something. Just make sure it gets accounted for, okay? Give me a sec just to copy this. Okay. All right, so this whole integral is going to expand into uv, so 1/5 e to the negative 3x sine 5x minus the integral of v du. So again, we've got a negative 3/5. Let's bring the negative 3/5 out. That'll make that positive 3/5. And then I've got e to the negative 3x sine 5x dx. Okay. And I know this is getting crazy, weird, and sloppy, but this is the integral that we started with. And we didn't do anything wrong. Sometimes you wind up with the integral you started with if you do parts twice and you swap the roles of u and dv. But we didn't do that. We didn't make any mistakes, and we still landed on what we started with. So we get to combine like terms. On the left-hand side, we have this whole original equation, integral. And then on the right-hand side, we have, now let's be careful, we have a negative 9/25 of the original integral, the same exact integral. So if on the left we have one of these guys, and on the right we have a negative 9/25, I'm just going to add 9/25 of this integral to both sides. So now I have over here, well, 1 and 9/25. So add the, what did I say, 9/25 of this integral over to the left-hand side, and we'll have 34/25 of this integral. Sorry, sine 5x, right? And on the right-hand side, I have just this guy. Minus 3/25 that's gone. That had made it over to the left-hand side. Cool. So now technically all you got to do is multiply both sides by 25/34, and you're all set. The integral of e to the negative 3x sine 5x equals 25/34 times this. So we're going to have what, negative 5/34 e to the negative 3x. And then the 25's just cancel, right? What we have, 3/34. I know we didn't actually integrate anything other than the dv's to v, but we still have our answer. So let's check a plus c on there and we're all set. All right, there you go. Okay, the last request that I got was for number 43. I'm sure the arc cosine is screwing you up. Another problem is there's only one thing here, so kids kind of get a little messed up because they don't realize there really are two things. So you struggle to find a u and a dv. We did do an example like this in the last video. That's when we integrated just the natural log of x. It looks like there's only one thing there. You let u equal your log x, and that means your dv has to just get the dx part and nothing else. So same thing is going to happen here. The only thing we actually have here is arc cosine. So I'm just going to let that be my u. That means the only thing left to let dv equal is dx. Differentiate u and we'll get, I'm sure you would look this up. It's in on the inside cover of your book, or you can just flip to the arc-trig section of integration, whatever section that was. Negative the derivative of the input here, which is just 1, over the square root of 1 minus the argument here squared. If you had to look that up, that's fine. It makes you human. And the integral of this is just going to be x. Okay, that was easy. So let's just see what the heck happens here. We are going to expand this to uv, so x arc cosine x minus the integral of v du. So I have, let's just throw the negative out on the front there and make that positive, and then I have x over this thing. Okay? Now how do we deal with this integral? Oh, I should probably put this on here. And technically I'm not crazy about this syntax. I am going to have to remember that when I evaluate at the end, 0 and 1/2 are going to have to be plugged into this as well. So let's see. It's not one of the arc functions. I think it's just going to be some simple u substitution. If I let u equal the radicand here, 1 minus x squared, then du is negative 2x dx. Well, I can make that happen, negative 2x dx. And let's fix it with a negative 1/2 out front. So if you want to formalize this, I don't want to take up too much room here. Let me just show you that this integral is going to become u to the negative 1/2, because we have a root u all the way on the bottom. Just bring it up and call it negative 1/2, and then the negative 2x dx all becomes du. So you see that this just becomes u to the positive 1/2 divided by 1/2 and then turn u back into this stuff. So 2 times u to the 1/2 obviously they cancel. And now I'm going to go ahead and plug in 1/2 and 0. Let's plug in half in. Let's see, where's the cosine 1/2? That's going to be a pi over 3. Minus 1 minus 1/2 squared, so 1/4. We'll take the square root of that. And let's plug in 0. That's easy. 1 minus 0 is 1. The square root of that is just 1. That part was easy enough. And now let's clean this thing up. We've got pi over 6 minus 3/4. So root 3 over 2. Take the square root of 3/4. You're going to get root 3 over 2 plus 1. So that's ugly. I'm just going to leave it like that. We got an irrational number. We got another irrational number, root 3 over 2. And yeah, that's good enough for government work right there. There you go. So if you guys have any other follow-up questions on any of the other problems, just don't hesitate to reach out. All right. Hope you guys are doing okay. We will have a quiz on this stuff next week. Okay.